Good morning everyone, good morning. I welcome you all to the Vedantu JEE English. Hope you guys are doing great, having a good time. Well people, if I'm audible and visible to everyone, let me know in the chat box with the thumbs ups. If I'm audible and visible to everyone right here. Let me know in the chat box if I'm audible and visible to everyone. Hi Sangeeta, hi Shreya, hi Sneha, hi Ashita. Hello Vani JD. Hi Devadatta. Hello Koramati. Hi Sudan. Welcome guys, welcome to the session, welcome to the session. I'm doing wonderful, I'm doing wonderful, I'm doing wonderful. Good morning Lennon, good morning. Hello Sneha. Hi Sham, hi Rishabh, hi Rohan, hi Arya. What's up, how are you guys doing? How are you guys doing? I'm great, Sham Kumar. Welcome to the session, welcome to the session. Wonderful guys. So, as you all must be knowing, today we are going to do the one-shot series from the chapter Electrochemistry. Yes? People, let me tell you, I have come up with 40 questions which we are going to solve in the today's session, which is going to revise your whole electrochemistry chapter, okay? I'll come up with exactly 40 questions which will be solving right here in this session, by means of which your entire electrochemistry will be revised. Yes? Are you guys super excited for that? Yes, exactly. Are you super excited for that? Are you super excited for that? Well, Ashita, it's not menti. It's not menti. Yes, Rishabh, theory will be also done. First theory part, then the numericals. Theory, numericals, and so on, yeah? Yes, are you super duper excited for that? Let me know in the chat box with the thumbs ups. Let me know in the chat box with the thumbs ups if you guys are super duper excited for that. How is the Josh? I just want to see the Josh of the session first, yeah? Yes, Josh is high. Is that? Wonderful. Nishan, basic bhi cover ho jayega. Chill bro, chill. Relax. Yeah? Okay, so people, before starting the session, let me introduce myself. As you all must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. Yes? Okay, so this is the schedule of the week which I'll be following in this Vedantu JEE English channel. Yes? So people, right now we are going to do the complete electrochemistry in one shot, right? At 5:30, today only, we are going to do chemical kinetics part 3. Correct? On Wednesday, that's tomorrow, we are going to do chemical kinetics part 4, then part 5 and previous equations from JEE Mains, yeah? From the chapter chemical kinetics, right? Okay, so for the ones who have not liked the video yet, do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Okay, so people, should we start the session? Should we start the session? Should we start the session? Let me know in the chat box. Give me the thumbs ups. Let me see the Josh first. Yes. Yes. Let's get started with the complete electrochemistry in one shot. Yeah? Yes. All right, guys. So let's get started with the first question, which is on our screen. Let's get started with the first question, which is on our screen. People, as I told you, I've come up with 40 different questions which will be solving in the today's session, by means of which your entire electrochemistry will get revised, yeah? Okay, so let's try to do the basic question which I'll come up right here, which is your question number 1, okay? Which is the strongest oxidizing agent, okay? So first of all, what oxidizing agent is all about? Oxidizing agent is the one which oxidizes others, but itself undergoes reduction. So that substance which itself undergoes reduction is what we call as oxidizing agent, number 1. Okay? People, as you all must be knowing, increase in the oxidation state of the element is what we call as oxidation. Whenever for the element oxidation state increases, we say the element undergoes oxidation. And whenever for a particular element the oxidation state decreases, we say the element undergoes reduction. I hope you all know that, yeah? Okay. Now guys, see. What are we supposed to check? We are supposed to check which of the following is the strongest oxidizing agent right here. Oxidizing agent is the one which oxidizes others but itself undergoes reduction. Yes? Now people, we are given with some values right here. Okay? See, if I ask you what is the charge present on this A right here, it's going to be 0. What is the charge present on this A right here? It's +1. Can I say the oxidation state of A is increasing from 0 to +1? If the oxidation state of A is increasing, so A is undergoing oxidation. So can I simply say this is the standard oxidation potential of electrode A? Yeah. So I got to know one thing. This is the standard oxidation potential value of electrode A right here. Yes. Similarly, the charge present on this B right here is 0. The charge present on this B right here is -1. Oxidation state of B is decreasing. Decrease in the oxidation state is what we call as reduction. So this is the standard reduction potential of B which is given to me. This is the standard reduction potential of B electrode which is given to me. Yeah. Similarly, guys, if you check this one, the charge present on this C is +1. The charge present on the C right here is 0. So can I say the oxidation state of C is decreasing? Decrease in the oxidation state is what we call as reduction. So this is again your standard reduction potential value of electrode C. Yeah. Now what we are supposed to check? We are supposed to check which one of the following is the strong oxidizing agent. That one among the following will be the strong oxidizing agent which will easily undergo reduction. Now, which one will be easily undergoing reduction? That one will be easily undergoing reduction, which will be having the maximum standard reduction potential value right here. Okay. So people, this is the standard reduction potential value. This is the standard reduction potential value. This is the standard oxidation potential value. So let me convert it into standard reduction potential. And how do we convert SOP into SRP for a particular element? We just reverse the sign. So standard reduction potential of A electrode is -1.1. Standard reduction potential of B electrode is 3.1. Standard reduction potential of C electrode is 4.1. Now, which one among the following is having maximum standard reduction potential? So this C is having the maximum standard reduction potential. So it will easily undergo reduction. If it is undergoing reduction easily, it will be a better oxidizing agent or strong oxidizing agent. So C is the one which is going to be the strongest oxidizing agent among all. Yes? Right? Wonderful. This was the first question which you would have solved properly right here. Yeah? Let's move on to the second question which is on our screen. I want all of you to give it a try. Let me know the answer in the chat box. Let me know the answer in the chat box. The question is based on the same concept. The question is based on the same concept. Let me tell you one important thing right here. First of all, more the value of standard reduction potential of the element, easily the element undergoes reduction. If easily the element undergoes reduction, that means it's going to be the better oxidizing agent. Yes? Better oxidizing agent, right? Similarly, more the value of standard oxidation potential of the element, easily the element undergoes oxidation. If easily the element undergoes oxidation, I'll say it's going to be a better reducing agent. Yes, better reducing agent. These two things you are supposed to remember. That's it. You're done. You're done with these sort of questions. Yes? Absolutely, Sudan. You have to include the sign as well. Yes, yes, yes. You'll be including the sign as well. Yes, absolutely. Okay. Now see guys, what we are supposed to calculate in the question. See, which one is the strongest reducing agent? Which one is the strongest reducing agent? I'll simply say reducing agent is the one which reduces others. But itself undergoes oxidation. Yes. But itself undergoes oxidation. I'll say among these four, that one will be the better reducing agent. That one will be the better reducing agent which easily undergoes oxidation. Now, which one among the following will easily undergo oxidation? I'll say that substance among these four will easily undergo oxidation which will be having the maximum standard oxidation potential. For the element to get oxidized easily, it should have more standard oxidation potential value, right? Now first of all, if I check the first option and the fourth option, already this magnesium has lost 2 electrons. So this is not going to get oxidized. It is not going to act as the reducing agent right here. Similarly, already this iron has lost 3 electrons. It's already in its maximum oxidation state. So it's not going to lose further more electrons. So it's not going to act as the reducing agent right here. So the answer must be between these two. Answer must be between these two. Now, among iron and magnesium, that one will be the better reducing agent, which will have the maximum standard oxidation potential. Yes, which will have the maximum standard oxidation potential, right? Right? See guys, let's get to know among iron and magnesium, which one is having the maximum standard oxidation potential. Where is iron? For iron, I need to consider this reaction. For magnesium, I need to consider this reaction. First of all, are these reactions the oxidation reactions or reduction reactions? These are the reduction reactions because electrons are being gained right here. So, which potentials these are? I'll say these are standard reduction potentials right here. So let me convert them into standard oxidation potentials. Standard oxidation potential of iron is going to be 0.04. I just reverse the sign. Standard oxidation potential of magnesium is going to be 2.37 volts right here. Now, which one among the two is having more standard oxidation potential? I'll say magnesium is having more standard oxidation potential, and that element which will be having more standard oxidation potential, that will easily undergo oxidation, and the substance which easily undergoes oxidation, that will be the better reducing agent. So I'll say magnesium is the one which will be the better reducing agent right here. Yes? Right? Wonderful, guys. Let's move on to one more question. Which is on our screen. Understand, guys. Calculate the oxidation potential of the following half cell. We are supposed to calculate the oxidation potential of the following half cell. Either you call it as half cell or you call it as electrode. One and the same thing, yeah? How do I calculate the oxidation potential of this electrode which is given to me? Understand one important thing. If I ask you what is the charge present on this iron right here, you should simply say 0. Yeah? If I ask you what is the charge on this iron right here, you should say +2. Is the oxidation state increasing or decreasing? Oxidation state is increasing. Increase in the oxidation state is what we call as oxidation. And for this electrode, I'm supposed to calculate its oxidation potential. Remember, whenever we are supposed to calculate the oxidation potential or reduction potential of any electrode under non-standard conditions, I will be always using the Nernst equation, okay? And what will be my Nernst equation all about? Nernst equation right now will be simply equal to oxidation potential of the electrode is equal to standard oxidation potential of the electrode minus 0.0591 divided by N, and it's going to be log of QC. Now, what these terminologies are right here in this equation, we need to understand that, yeah? Understand, guys, see. First thing, I'm given with the electrode right here and I need to calculate its oxidation potential. So in order to calculate the oxidation potential of this electrode right here, this electrode must behave like the anode, yeah? Correct? Now, what is the reaction which is going to happen when this electrode will act as the anode? I'll say Fe will get converted to Fe dye positive, Fe should get converted to Fe solid, should get converted to Fe dye positive aqueous, and with this, it should give 2 electrons. Okay, this is what I'll be calling as the oxidation reaction which will be happening at anode, right? Yes. Now people, how many electrons are being exchanged right here in this reaction? I'll say 2 moles of electrons are being exchanged right here. So I can simply say the value of N right here is equal to 2. N represents the number of moles of electrons exchanged in a chemical reaction right here. Yes, number 1. Number 2, if I want to write the reaction quotient expression, we already know how do we write. We already know how to write the reaction quotient expression. We know that, yeah? Very simple, guys. I'll be starting with the product which is in aqueous form. I'll simply say concentration of Fe dye positive divided by, this is solid, its active mass is taken as 1, if you remember. Yes. Now, guys, see, concentration of Fe dye positive in the equation is given as 0.1. So I got the value of QC as well. I got the value of N, I got the value of QC. I got the value of N, I got the value of QC. Now I'm in need of standard oxidation potential of this electrode. Now there is one more parameter which is given to me as per the equation. See guys, this parameter is given to me. Fe plus 2 changed to Fe solid. So oxidation state over here is plus 2, oxidation state over here is 0. Can I say oxidation state of iron is decreasing? Decrease in the oxidation state is what we call as reduction. So this is the standard reduction potential of this iron electrode right here. But in this equation, do I need the standard reduction potential of iron electrode or standard oxidation potential? I need definitely standard oxidation potential of iron electrode. And how do I represent the standard oxidation potential of iron electrode? Just reverse it. It's going to be Fe solid changed to Fe dye positive. Just reverse the sign. It's going to be 0.44 volts. Yes, I got everything. I need to put all these values into the Nernst equation. I'll be getting the value. Yeah. Very, very, very simple. Absolutely. So people, I can say something like this. Oxidation potential of the electrode will be equal to standard oxidation potential of the electrode, which is 0.44 volts, minus 0.0591 divided by, what is the value of N right here? Value of N right here is 2, and it's going to be log of QC. QC value I got to know as 0.1, which is simply 10 power minus 1. Now, can't we simply solve this question and get the value of oxidation potential, which we were supposed to calculate? Absolutely. It's going to be simply 0.44 minus 0.0591 divided by 2. Log of m to the power n is always equal to n log m. And we know log of 10 to the base 10 is always equal to 1. So people, you'll be getting the value of the oxidation potential of the iron electrode right here as 0.44 minus, this minus is going to come to the front. It's going to be plus 0.0591 divided by 2. Just solve this a bit and get the answer in volts, yeah? This is going to be the standard, this is going to be the oxidation potential of this iron electrode right here, which we were supposed to calculate, yeah? People, if this is the oxidation potential of the iron electrode, if I want you guys to calculate its reduction potential, can we do that? I just have to reverse the sign of it. I'll say reduction potential of the same iron electrode is going to be minus times 0.44 plus 0.0591 divided by 2 volts, yeah? The question is done and dusted, right? The question is done and dusted, yes? Wonderful, guys. I hope you got it. Let me know in the chat box if you got it so that I can move on to the next question. Let me know in the chat box if you got it so that I can move on to the next question. Yes? Done and dusted, right? Okay, so people are getting the answer as 0.46. So you are getting the value of oxidation potential as 0.46 volts. So reduction potential is simply going to be minus 0.46 volts. Yeah, very, very, very simple. Okay, let me move on to one more question, guys, which is on your screen now. Calculate the oxidation potential of the following half cell. I'm again given with the half cell. Either you call it as half cell or you call it as electrode, one and the same thing. Yes, and I am supposed to calculate the oxidation potential of this electrode right here. Okay, so if I'm supposed to calculate the oxidation potential of this electrode right here, then this electrode should be acting like the anode so that oxidation takes place. Yeah, absolutely right. Now people, how to solve this sort of equation? Understand, I'm supposed to calculate the oxidation potential of the following half cell right here. If I ask you, what is the charge present on this chlorine right here? What is the oxidation state of chlorine right here? You should simply say 0, yeah? If I ask you, what is the oxidation state of chlorine right here? It's -1. Can I say oxidation state of chlorine is decreasing? Yes. Decrease in the oxidation state is what we call as reduction. Yes. So people, I'm supposed to calculate the oxidation potential. Am I supposed to reverse the cell? What do you think? What do you think? Let me know in the chat box. Am I supposed to reverse the cell? Yeah. In order to calculate the oxidation potential, I'm supposed to reverse the cell so that I can write the proper oxidation reaction right here. Yes. Absolutely. Let me reverse the cell a bit. It's going to be HCl, whose concentration is 0.1 molar. It should change to Cl2 gas, whose pressure is 10 atm right here. Correct? Yes. Now this is the proper representation of the electrode if it has to behave like the anode, yeah? And if it is behaving as the anode, at anode we already know oxidation takes place, yes? So right here there should be loss of electrons, right? So people, what should be the reaction at anode? What should be the reaction at anode? This chlorine right here is in the form of Cl negative. This chlorine, it is in the zero oxygen state right here. So can I say the reaction should be like this? 2 times Cl negative should change to Cl2 gas plus 2 electrons. Can I say this is the oxidation reaction right here, which will be happening at the electrode when it will be behaving as the anode? Yes, absolutely right. Yeah. Very, very, very simple. Now guys, I got the reaction which is taking place at anode. How many moles of electrons are being exchanged right here? 2 moles of electrons are being exchanged. So I can say the value of N right here is 2. Yes. Now guys, can I write the expression for reaction quotient? It's going to be Cl2 is present in the gaseous form. So for the gases, we use the term partial pressure. So I'm writing partial pressure of Cl2 to the power stoichiometry coefficient, that is 1, divided by the Cl negative will be in aqueous form. So concentration of Cl negative to the power stoichiometry coefficient, that is 2. What is the partial pressure of Cl2 which is given to me as per question? It's going to be 10 atm divided by. What is the concentration of Cl negative? It is simply 10 power minus 1. Yes, it is simply 10 power minus 1, 0.1, yeah. It's going to be 100 right here. So can I say I got the expression for QC, I got the QC value right here as 100. Yes, people, I got the value of N, I got the value of QC. Now, in order to calculate the oxidation potential, as per Nernst equation, I should be using this equation. It's going to be E naught of oxidation minus 0.0591 divided by N, and it's going to be log of QC right here. Yes. So people, I got the value of QC, I got the value of N. I should know the value of standard oxidation potential right here. Yes. Did I miss something right here? Yes, I missed something. Just a second, guys. I missed something. It's going to be, this is square also right here. Yes, it's going to be 10 divided by 10 power minus 2. Yes, it's going to be 10 power 3. Yeah, now it's perfect. Yes, now it's perfect, right? Okay, so people, in order to calculate the oxidation potential of the electrode, I should be knowing the value of QC, I should be knowing the value of N, I should be knowing the value of E naught oxidation. Yes, so it's time to get the value of the standard oxidation potential of the electrode. There is something which is given to me. Have a look. Chlorine in Cl negative, oxygen state minus 1. Right here the oxygen state 0, minus 1 to 0. Increase in oxygen state. Increase in oxygen state is what we call as oxidation. So can I say this is the standard oxidation potential of chlorine electrode which is given to me? Yes. Exactly, guys. Standard oxidation potential of this electrode is given to me, minus 1.36 volts. Can I say I've got everything right here? I can simply put all the values into the equation. I'll be getting the oxidation potential of electrode as E naught OX. E naught OX is minus 1.36. Yes, minus 0.0591 divided by value of N. Value of N we got to know as 2. It's going to be log of QC. QC value we got to know as 10 power 3. Yes. The question is done and dusted, guys. The question is done and dusted. It's going to be minus 1.36. This is going to be minus 0.0591 divided by 2 log of m to the power n, which is going to be n log m. Log 10 value is 1, as you all must be knowing. Just solve this part. You'll be getting the answer in volts. Yeah. Let me know the exact answer which you are getting from here. Yes, Vijay, this is enough. This is enough. This is enough. Yes. Let me know the exact value which you'll be getting here, which you'll be getting from here. Let me know the exact value in the chat box fast. I'm waiting for your answers. Let me know. Let me know. Is it coming as minus 1.44? All right. So I'm getting the value as minus 1.44 volts right here. So what is this value all about? This is the oxidation potential of this electrode which I was given with. If this is the oxidation potential, can I calculate its reduction potential as well? Yes. I just need to reverse its sign. That's it. The question will be again done and dusted, right? This is the oxidation potential of the electrode. If you were supposed to calculate the reduction potential, you were supposed to reverse its sign. So after reversing its sign, that will give you the value of the reduction potential right here. Yes? Wonderful. Wonderful, guys. Great. So should I move on to the next question? Let me know in the chat box. Let me know in the chat box if this is done. If this is done, let me know in the chat box fast. Jaldi batao. Yes. Should I be moving on to one more question right here? Wonderful, guys. So let's move on to one more question which is on our screen right here. See, guys, again the same type of question. Calculate the oxidation potential of the following half cell. Half cell matlab electrode. Yes, we are supposed to calculate the oxidation potential of this electrode right here. People, if you would have noticed one thing, can I say I can write this cell like this as well. H2 gas whose pressure is 10 atm. Instead of HCl, I can write H positive whose concentration is 0.1 molar. Yes. Can I say this is the hydrogen electrode which is given to me? Yes. This is the hydrogen electrode, and people, standard oxidation potential as well as standard reduction potential of hydrogen electrode is always taken as 0 as the reference, if you remember. Yes, so I can say the standard oxidation potential or standard reduction potential of the hydrogen electrode is always taken to be as 0. Yes, right? Now, what are we supposed to do? What are we supposed to do? Understand. We are supposed to calculate the oxidation potential of this electrode. If we are supposed to calculate the oxidation potential of the electrode, should this electrode be behaving as the anode? Absolutely, because at anode oxidation takes place. So in order to calculate the oxidation potential of the electrode, I want this electrode to behave as the anode, right? So if the electrode behaves as the anode, what is the reaction which should take place at this electrode? I should say oxidation reaction should take place, yeah? Yes. Now, what will be the oxidation reaction of this hydrogen electrode all about? It's simply going to be H2 gas should get converted to 2 times H positive aqueous, and with this, you'll be getting 2 electrons right here. This will be the oxidation reaction which will be taking place at the anode if this electrode is behaving like it, yeah? Yes. Now, what is the value of N which we got right here? See guys, 2 moles of electrons are being exchanged right here. Yes, so the value of N we got as 2. If the value of N is 2, can I calculate the value of QC as well? I'll be starting from the product. Yes. See guys, this is H positive, aqueous. Yes. So I'll be simply writing the concentration of H positive raised power 2 divided by this in gaseous form. So I'll be using its partial pressure raised power stoichiometric coefficient, that is 1 again. Yes. Now guys, what is the concentration of H positive which is given to me? It's given to me as 10 power minus 1. So it's going to be 10 power minus 1 ka square divided by partial pressure of H2 gas which is given to me as 10. Yes. So it's going to be 10 power minus 2 divided by 10. So it's going to be 10 power minus 3 right here. I got the value of QC, I got the value of N. I got the value of QC, I got the value of N. Number 1. Yeah. Now guys, E naught oxidation, E naught reduction, which we already know that's always 0 for the hydrogen electrode. I can simply use the Nernst equation. I can get the oxidation potential of this electrode under non-standard conditions. It is going to be E naught oxidation minus 0.0591 divided by N, and it's going to be log of QC. Yes? Right? This value is equal to 0. So you'll be getting the answer as minus 0.0591 divided by N value you got to know as 2. It's going to be log of QC. QC is simply 10 power minus 3. Yes. So you're getting it as minus 0.0591 divided by 2. Log of M to the power N is N log M simply. Minus 3 log 10 is 1. So just solve this value. You'll be getting the value in volts right here. Yes. So what is the exact answer coming, guys? Let me know in the chat box. What is the exact answer coming? What is the exact answer coming right here? Let me know. Let me know fast. 0.08 volts. Wonderful. So the oxidation potential of this hydrogen electrode under non-standard conditions right here is 0.08 volts. Yeah, which we were supposed to calculate. If the oxidation potential of hydrogen electrode came out to be 0.08 volts, can you let me know what is going to be the reduction potential of the same hydrogen electrode? We just need to reverse its sign. So I'll simply say reduction potential of the same hydrogen electrode is going to be minus 0.08 volts. Yeah. Yes, exactly. All of you are perfectly correct. Yeah. Yes. Wonderful. So should I move on? Should I move on to the next question? Let me know in the chat box. Let me know in the chat box. Should I be moving on to one more question? Should I be moving on to one more question? Let me know in the chat box. Yes. Thank you, Gagan. Thank you. All right. So let's move on to one more question, which is on our screen. Okay. See guys what this question is all about. A solution containing 4 into 10 power minus 4 molar Cr2O7 dinegative and 2 into 10 power minus 2 molar Cr tri-positive ions shows a pH of 1. That means the solution is acidic. Yeah. Absolutely. Calculate the reduction potential of the following half cell. We are supposed to calculate the reduction potential of the following half cell. Yes. Now guys, how to do it? Understand what I'll be doing right here. See guys, the reaction which is given to me, that is Cr2O7 dinegative, is getting converted to what? Is getting converted to Cr plus 3 right here. Okay. So first of all, I'll say the oxidation state of chromium right here is +6. The oxidation state of chromium right here is +3. Is the oxidation state of chromium increasing or decreasing? It is decreasing. Decrease in the oxidation state is what we call as reduction. Yes, decrease in the oxidation state is what we call as reduction. And reduction simply means gain of electrons. Yes, reduction simply means gain of electrons. Now, how many electrons are being gained by this Cr2O7 di-negative right here? How will I be calculating that? Just calculate the change in the oxidation state of chromium. This is the final oxidation state of chromium minus initial oxidation state of chromium. The change in the oxidation state of chromium is going to be 3. But that 3 is going to be the change in the oxidation state for 1 atom of chromium. But I have 2 atoms of chromium. Yes, for 1 atom of chromium, change in the oxidation state will be 3. Or I'll say one atom of chromium is going to gain 3 electrons. So 2 atoms of chromium are going to gain 6 electrons right here. Yes. And people, for this reaction, we are given with the E0 value. So which E0 right here is? I'll say this is the standard reduction potential value of the electrode whose cell reaction is this one. Yes. So I'm given with the standard reduction potential value of the electrode whose cell reaction is this, is given to us as 1.5 volts here. Right. Now guys, if I ask you, is the reaction balanced or not? What do you think? I think the reaction is not balanced, yeah? So let's try to balance it first, yeah? Let's try to balance it first. This should be 2 times, and we know the reaction is taking place in acidic medium because the pH of the solution is 1. Yes, the pH of the solution is 1. So how do we balance the reaction in acidic medium? How do we balance the redox reaction in acidic medium? Do you remember that? Do you remember that? Very simple, guys. First of all, I have balanced the electrons. Yes. Now over here we have got 7 oxygen atoms. So in order to balance the oxygen atoms, I'll be adding the requisite number of water molecules right here. I added 7 water molecules in order to balance the oxygen atoms. Yes. Now after this, I need to balance hydrogen as well. Yes. So people, right here on the right hand side, we have got 14 hydrogens. So over here, I'll be adding 14 H positives. Then only the reaction will get balanced. Now the reaction is balanced completely. Yeah. The reaction is completely balanced, right? People, how many electrons are being exchanged right here in this reaction? I'll say 6. So the value of N right here is simply equal to 6, yeah? Yes? Saad will be doing, I told you, we'll be doing 40 questions, and from those 40 questions, whole electrochemistry will get revised, yeah? Alright, Fazan, I'll be doing that as well. Now, people, since I got the value of N, can I write the expression for QC? I can write it, yes. This Cr tripositive in aqueous form, this is in pure liquid form, this is in aqueous form, this is in aqueous form, yes. See, guys, this is the ion which is in aqueous form, this is one more ion in aqueous form, this is one more ion in aqueous form, this water right here is in liquid form, yes. QC expression is simply going to be concentration of Cr plus 3 raised power the stoichiometry coefficient divided by, since it is in pure liquid form, so its active mass will be 1, divided by concentration of Cr2O7 di-negative raised power the stoichiometry coefficient, that is 1, multiplied by concentration of H positive to the power 14 right here. Yes. Now people, do we know the concentration of H positive over here? We do not know the concentration of H positive. For that, pH of the solution is given. Yes. pH of the solution is given to us as 1. Can I say pH is nothing? pH is just minus log of H positive concentration to the base 10. It's given as 1. Take this minus on the other side. It's going to be, I'm writing it like this. Log of H positive concentration to the base 10 is equal to minus 1. So I'll be simply writing H positive concentration in the solution is going to be 10 power minus 1. Yeah? It's going to be 10 power minus 1, right? Done? I got the H positive concentration. Now guys, I can simply write the expression for QC, which is going to be, or let me write it right here so that I get some space to write more. Concentration of Cr tripositive. Is it given to me in the question? Is it given to me as per the question? Yes, the concentration of Cr tripositive is given to me. That is 2 multiplied by 10 to the power minus 2. Raised power what? Raised power stoichiometry coefficient 2 divided by. Is the concentration of Cr2O7 di-negative given to me? Absolutely. It is 4 multiplied by 10 power minus 4. Is the concentration of H positive given to me? I got to know that is 10 power minus 1. So it's 10 power minus 1 raised power 14 right here. So can I say this term and this term will get cancelled out? Yes. So I got the QC value right here as 10 power 14. People, I got the QC value. I know the value of N. Now it's high time to get the value of what? To get the value of standard reduction potential, which is already given to me right here. Yes, now, what am I going to do? I am going to use the Nernst equation. I'm going to use the Nernst equation, absolutely, right? I'll be writing the reduction potential of the electrode whose cell reaction is this one is going to be standard reduction potential of the same electrode, which is 1.5 minus 0.0591 divided by the N value we got to know that is 6 log of QC value we got to know as 10 power 14 right here. Yes, we just need to solve this one. Yes. Absolutely, guys, we are done with the equation. The equation is done and dusted. Let me know the exact value of reduction potential, guys, in the chat box, which you are getting by solving it. So you'll be getting the reduction potential of the electrode will be equal to 1.5 minus 0.0591 divided by 6, and it's going to be log of 10 power 14, log of m to the power n, which is going to be n log m, so 14 comes to the front, log of 10 is 1. Just solve this value and let me know the answer in the chat box exactly. So people are saying the answer is coming as 1.36 volts. Is that Vijay? Wonderful. So reduction potential of the electrode is simply going to be equal to how much? 1.36. All right. The reduction potential of the electrode is going to be 1.36. If you were supposed to calculate the oxidation potential of the electrode, what you were supposed to do? You were simply supposed to reverse the sign of it, yeah? Yes? Sorry. Yes. Suzanne, you can do one thing. You just take the video a little back. It'll be automatically a replay, yeah? Just take the video a little back. It'll be automatically a replay, yeah? Should I be moving on to one more question, guys? Let me know in the chat box. This question is dusted right here. Let me know in the chat box if you want me to move on right here. Should I be moving on to one more question? Let me know in the chat box fast. Yes. Yes. Wonderful. Let's move on to one more question then. Let's see how this question is to be solved. See, guys, again a very simple question. Again a very simple question, right? A zinc electrode, a zinc rod basically is dipped in 0.1 molar solution of its salt at 25 degrees centigrade. Assume the electrolyte is 20% dissociated. Calculate the electrode potential. Whenever it's not clearly mentioned which potential you are supposed to calculate, we are going to calculate the reduction potential of that at that time, okay? Whenever in the question it won't be clearly mentioned that whether you are supposed to calculate the oxidation potential or reduction potential, so remember at that time you'll be calculating the reduction potential, yeah? Right? So right here what we are supposed to do, we are supposed to calculate the reduction potential, yes? Now first thing, am I given with the standard reduction potential of zinc? Just check it out. The zinc is right now in +2 oxygen state, right here in 0, +2 to 0, decrease in oxygen state, decrease in oxygen is what we call as reduction. So this value is the standard reduction potential of zinc right here. Yes? Yes? Can we solve this one, guys? Can we solve this one? Absolutely. See what is given in the question. We have got a rod basically, we have got a zinc rod, and I'm going to dip this zinc rod into a solution which contains the salt of zinc, For example, I've used the solution as ZnSO4. Whose concentration is given to us as 0.1 molar. Yes. So people, this ZnSO4, it will be completely dissociated into its ions. Is that? Right here, it's mentioned in the question, assume the electrolyte is 20% dissociated. So I'm not supposed to dissociate this electrolyte completely into its ions, yeah? So what I'll be doing, I'll be writing something like this. Zinc sulfate, it will be converted into Zn di positive definitely and SO4 di negative aqueous ions. Yes. So people, if you remember, let's say at time t is equal to 0, the concentration of ZnSO4 is C. It's going to be 0. This is going to be 0. The concentration of ZnSO4 at time t is equal to 0 is given to me as 0.1, which is 10 power minus 1. Let's say the degree of dissociation is alpha. Yeah. So can I say after some time when 20% of the electrolyte would have got dissociated into its ions, can I say I'll be left with C minus C alpha right here, and this is going to be C alpha, this is going to be C alpha. Yes. People, we are given in the equation, assume the electrolyte to be 20% dissociated. Remember, alpha is always equal, degree of dissociation is always equal percentage dissociation divided by 100. So alpha value is going to be 20 divided by 100, which is simply going to be 0.2. So I know the value of alpha, I know the value of alpha, I know the value of C. So people, in the container, can I say when the 20% of the electrolyte would have got converted into its ions, the concentration of Zn di positive will be C alpha, the concentration of SO4 di negative will be C alpha. So I'm going to write something like this: the concentration of Zn di positive in the container when 20% of the electrolyte would have got dissociated will be equal to C multiplied by alpha. C value is 10 power minus 1 multiplied by alpha value we got to know, that is 2 into 10 power minus 1. Yes, so I got the concentration of Zn di positive in the container as 2 multiplied by 10 power minus 2. So this is the concentration of Zn di positive in the container. Yes, right? Right? Now guys, what are we supposed to calculate? We are supposed to calculate the reduction potential. For the zinc, in order to calculate the reduction potential of this zinc electrode right here, I should say the zinc should behave as the cathode. Yeah? So that reduction takes place, so that we can use that reaction, so that we can get the N value. Yeah? So people, in order to calculate the reduction potential of this electrode, this zinc electrode right here should be behaving like the cathode, and if the zinc is behaving like the cathode, I'll say reduction reaction has to take place, and the reaction should be somewhat like this: Zn di positive aqueous plus 2 electrons, it should get converted into Zn solid. Yes, this is the reaction which should take place in this electrode when this electrode will be behaving as the cathode. Yes, right? Now, people, how many electrons are being exchanged right here? Can I say 2 electrons are being exchanged, 2 moles of electrons are being exchanged right here? So can I say the value of N is equal to 2? Can I say the value of N is equal to 2 right here? Yes, absolutely. So can we get the QC value right here? Can I say QC value is going to be equal? I'll be starting from the product. Product right here is in solid form. For the substance which will be in pure solid form, its ectomass is taken as constant, which will be taken as 1 divided by concentration of Zn di positive in the solution. Yes, people, concentration of Zn di positive in the solution we got to know as 2 multiplied by 10 to the power what? 10 to the power minus 2. So 1 by 2 is nothing, that is 0.5, and this is going to be 2, so it's going to be 50. So I got the value of QC right here as 50. Yeah, I got the value of QC, correct? Now I got the value of QC, I got the value of N. I'm given with the standard reduction potential. Can I simply calculate the reduction potential by means of the Nernst equation? The reduction potential of the electrode is going to be equal to E naught RAD, standard reduction potential, minus 0.0591 divided by N, and it's going to be log of QC right here. Yes? Yes, I can write it. So standard reduction potential of the electrode is given to me as minus 0.76. Yes, minus 0.76, minus 0.0591. Do I know the value of N right here? Absolutely, I know the value of N, that is 2. Log of QC, QC value. What is the value of QC that's given to me? That is 50. Yes, people, just solve it. Let me know in the chat box. Let me know in the chat box what is the exact value which you are getting right here, right? Let me know in the chat box the exact value of the reduction potential of the zinc electrode right here. Do it, give it a try. Let me know the exact value of it. You can simply use log of 50 as log of 5 multiplied by 10. Then you can use the property of log of m multiplied by n, which is going to be log of m plus log of n. Yeah. So Vijay is saying the answer is coming as minus 0.80 volts. All right. The answer is coming as minus 0. What? Minus 0.80 volts. So minus 0.80 volts is the reduction potential of the electrode which was given to us right here. Yes. So people, let me know in the chat box if it is clear to every single guy right here. If this is the reduction potential of the zinc electrode, can you let me know the oxidation potential of the same electrode? I just need to reverse the sign. I'll be getting the oxidation potential as well. Yeah. Yes. Right? Exactly, guys. Exactly. Wonderful. Yes, Arif, you'll be getting the PDF of these 40 questions. Yes. In the Telegram group. Yeah. Okay. So people, should I move on to one more question? Let me know in the chat box. Should I move on to one more question right here? Let me know in the chat box. Yeah. Yes. Okay. Let's move on to one more question which is on our screen. See guys, We are given with the standard reduction potential of copper. Yes, because Cu dye positive is getting converted to Cu. That means oxidation state is changing from +2 to 0. +2 to 0 means decrease in oxidation state. Decrease in oxidation state is what we call as reduction. So this is basically the standard reduction potential of the copper which is given to us. Yeah. Calculate the reduction potential at pH equal to 14. Calculate the reduction potential at pH equal to 14 for Cu dye positive getting converted to Cu electrode at 25 degrees centigrade, right? So we are supposed to calculate the reduction potential of the copper electrode right here. Can we do it? Can we do it? Yes, guys, but I'll be using small concepts of ionic equilibrium as well. Then only we can solve this question. Otherwise, we cannot solve this question. Yeah. See how the question is to be solved. Understand, guys. We are supposed to calculate the reduction potential of the copper electrode right here. If we are supposed to calculate the reduction potential of the copper electrode, I should say the copper electrode right here should behave as the cathode so that reduction will take place on it. Yes. So that reduction will take place in that electrode. Yes. So people, in order to calculate the reduction potential of the copper electrode, I want this copper electrode to behave as the cathode. And if this copper electrode behaves as the cathode, I should say the reaction that must take place at the cathode should be Cu dye positive plus 2 electrons should get converted to Cu solid. Yes, this is the reaction which must take place right here. Correct? Now guys, how many moles of electrons are being exchanged right here? I'll say 2 moles of electrons are being exchanged. Yes. So can I say the value of N right here is equal to 2? Absolutely. Absolutely, the value of N is 2. Right? So people, can I write the expression for QC? QC expression is going to be, this is in solid form, its active mass is unity, divided by concentration of Cu dye positive raised power stoichiometric coefficient, that is 1. Right? But in order to calculate QC, I need to have Cu dye positive concentration. Now the point is, where will I get that Cu dye positive concentration? Where will I get that Cu dye positive concentration? Understand. For that, I'm given with one important thing right here. Ksp of CuOH whole twice, it's given to me as 10 power minus 19. Yeah. And pH is given to me as 14. People, if pH is given to me as 14, what can I conclude from here? Can I say H positive concentration will be simply equal to 10 power minus pH? Yes. So it's going to be 10 power minus 14. I got the H positive concentration. Now at 25 degrees centigrade, if you remember, H positive concentration multiplied by OH negative concentration is always equal to 10 power minus 14 at 25 degrees centigrade, right? We know the H positive concentration, which is 10 power minus 14. Can I say OH negative concentration is going to be 10 power minus 14 divided by H positive concentration, which is again 10 power minus 14. The value is going to come as 1. So 1 is the concentration of OH negative, which I got right here. 1 is the concentration of OH negative. But what I need? Do I need concentration of OH negative? I need the concentration of Cu dye positive. For that, I'll use one more thing. CuOH whole twice, its Ksp is given to me, yeah? So I'm going to write something like this. CuOH whole twice. If it is Ksp is given to me, I'm going to break it into its ions. It's going to be Cu dye positive aqueous plus 2 times OH negative aqueous. Yes? Right? Can I write the expression of Ksp for this CuOH whole twice right here? It's going to be simply concentration of Cu dye positive multiplied by concentration of OH negative raised power 2. Yes? People, is the value of Ksp given to me? Yes, Ksp of this thing is given to me as 10 power minus 19. Will be equal to concentration of Cu dye positive multiplied by concentration of OH negative, that is 1. So I got the concentration of Cu dye positive simply as 10 power minus 19. Yes, absolutely. So it's going to be 1 divided by 10 power minus 19. So can I see the value will be coming as 10 power 19 right here? This is the value of QC which I got. This is the value of QC which I got, absolutely, right? Now, I got the value of QC. I know the value of N. Do we know the standard reduction potential of the copper electrode? Yes, we know that. So I can simply use the Nernst equation. I can write reduction potential of the copper electrode will be equal to E naught RED, standard reduction potential of copper electrode, minus 0.0591 divided by N, and it's going to be log of QC right here. Yes. So people, E naught RED, standard reduction potential of copper electrode is given to me as 0.34 minus 0.0591 divided by N. N value we already got to know, that is 2, and it's going to be log of 10 power 19. Now use the property of log 10 power 19. Log of m to the power n. N log m, yes? Yes. Let me know the exact value which you are getting right here. Let me know the exact value from here, guys. Let me know the exact value in the chat box. 0.0591 divided by 2 log of m to the power n is going to be n log m. Log 10 is 1. Just solve this part and let me know the exact value of it in volts, yeah? Let me know the exact value which you'll be getting from here. Let me know fast, let me know fast, let me know fast. I'm waiting for you. Let me know fast. Let me know fast. Yes. Let me know what is the exact value which you are getting from here in the chat box. Vijay is saying the answer is coming as minus 0.22 volts. All right, I trust you, Vijay. Minus 0.22 volts is going to be the reduction potential of this copper electrode right here. If you got the reduction potential of this copper electrode, can we calculate its oxidation potential as well? Can I say I just need to reverse this sign? That's it. I just need to reverse this sign. That's it. In order to calculate the oxidation potential of the same copper electrode. Yes. Yes. People, is the question done and dusted? Should I move on? Should I move on to the next question? Should I move on to the next question? Let me know in the chat box. Let me know in the chat box. Yes. Okay. Okay. Done and dusted, right? Let's move on to one more question which is on our screen. This is the question on our screen, guys. We can easily solve this one as well. See, guys, I'm given with the reaction which is actually the reduction reaction because electrons are being gained right here, which is actually a reduction reaction. The half cell potential means right here the reduction potential. Yes, the reduction potential of the electrode whose cell reaction is this one is minus 0.197 volts at pH 7. Calculate the half cell potential at pH equal to 6 when the concentration of CH3CHO is equal to this, Okay, let's get to know. Yeah, let's see how this question is to be solved. First of all, I'm going to write the conditions which are given to me as per the question. See, guys, the conditions which are given to me as per the question, when the concentration of CH3CHO, let me write it from here. When the concentration of CH3CHO is equal to the concentration of CH3CH2OH, both are equal to 1 molar, and pH at that time is equal to, at this time pH is equal to 7. So right here, at this time, the reduction potential value is given to me as how much? It's given to me as minus 0.197 volts, yeah? When I have kept the concentration of this and this right here is 1 molar, when I have kept the pH of the solution as 7, at that time, the reduction potential value is given to me as how much? It's given to me as minus 0.197, yes? Right? Calculate the half cell potential at pH is equal to 6. What are we supposed to calculate? We are supposed to calculate the reduction potential when the concentration of CH3CHO is equal to concentration of CH3CH2OH is equal to 10 power minus 5 at a pH of 6. So when the pH of the solution will be 6 and the concentration of this and this is 10 power minus 5 molar, I need to calculate the reduction potential at that time. Yes. So how to solve this sort of equation? Right? So people, let me make you understand the question. When the concentration of CH3CHO, CH3CH2OH is equal to 1 molar and pH of the solution is 7, at that time the reduction potential of the electrode is equal to minus 0.197. Yes. And now when the concentration of CH3CHO and CH3CH2OH both are equal to 10 power minus 5 molar and pH of the solution is equal to 6, what will be the reduction potential at that time? Can we solve this one? Absolutely, guys, it's a very simpler one. First of all, we are given with the reaction. Can I write the expression for QC for the reaction? First of all, I already know the value of N. N value is given to me as 2. Number of moles of electrons which are being exchanged right here, it's given as 2. Yes. I can write the expression for QC. Expression for QC is going to be equal to concentration of CH3COH, concentration of CH3CH2OH, raised power the stoichiometric coefficient, that is 1, divided by concentration of CH3CHO raised power stoichiometric coefficient, that is 1, multiplied by concentration of H positive raised power 1. Yes. Yes. Now people, if you can notice one thing right here, In both the cases, I'm keeping concentration of this one and this one as same. In both the cases, in the initial case, I'm keeping the concentration of both them as 1 molar, and in the later case, I'm keeping the concentration of both of them equal 10 power minus 5. Yes. So anyways, these two are going to get cancelled out. Yeah. So can I write it simply as 1 divided by concentration of H positive? Yes. Anyways, both of them are going to get cancelled out, right? Because I'm keeping the concentration of both these substances equal in both the cases. Yeah. I hope you got it. Now, I know the value of QC. I know the value of QC, right? If I know the value of QC, I know the value of N at the same time. I can use the Nernst equation. Let's see what is the Nernst equation all about. Let's see what is the Nernst equation all about. See, this H positive concentration ka square, because right here it is 2. Yes, it is H positive concentration ka square. Yeah. Right? Now guys, what will be the Nernst equation all about? It's going to be simply equal to reduction potential of the electrode will be equal to standard reduction potential minus 0.0591 divided by N, and it's going to be log of QC. QC value is given to me as 1 divided by concentration of H positive ka square. Yes, but people, I can remove this. I can write it like this. I can write it like this. Concentration of H positive raised power minus 2. Yes, I can do that. Now people, can I convert this equation into the form of pH? It's going to be reduction potential will be equal to standard reduction potential of the electrode minus 0.0591 minus 0.0591 divided by N value is given to me as 2. Yes, and it's going to be minus 2 log of H positive concentration. Yes, I can simply convert this equation in the form of pH. See guys how? See how I'll be converting it. Understand? I'll be writing reduction potential. I'll be writing reduction potential of the electrode is equal to standard reduction potential of the electrode, which is E naught minus RAD. I mean E naught RAD minus 0.0591, right? 0.0591. Can I say this 2 and this 2 would have got cancelled? Can I say minus log of H positive is what we call as pH? Minus log of H positive is what we call as pH. Yes. So people, I got the equation right here, the general equation right here as reduction potential of the electrode is equal to standard reduction potential minus 0.0591 multiplied by pH. Yeah. Now guys, I'm going to put these two conditions. Into the general equation which I got for this electrode whose cell reaction is this one. Yeah. Yes. Now. The question is done and dusted, guys. The question is done and dusted. See, this is the equation which I got for the electrode whose cell reaction is this one. Yeah. Now, if I use the first condition in my equation right here, reduction potential as per the first condition is minus 0.197 will be equal to E naught RAD, standard reduction potential minus 0.0591 multiplied by pH. pH in the first condition is given to me as 7. I'm calling this as equation number 1. Similarly, the second equation, instead of reduction potential, I'll be writing the reduction potential of the electrode when the pH is kept at 6. When the pH of the solution is kept as 6 is equal to standard reduction potential of the same electrode minus 0.0591 multiplied by pH, which is 6. Let's call this as equation number 2. Yes, people, we have two equations. Can we solve them up? Can we solve them up? Absolutely, we can do that. Yeah. We can do that, right? The question is almost done and dusted. The question is done and dusted right here. Yes. Now what I'll be doing right here? If I'll subtract second from first, it's going to be minus, this will be minus, this is going to be plus. Can I say this and this got cancelled? Can I say I got something like this, minus 0.197 minus reduction potential of the electrode when the pH of the electrode was kept as 6 is equal to 0.0591. I'm taking common. It's going to be 6 minus 7. Yes. 6 minus 7 is minus 1, so it's going to be minus 0.0591. Yes, minus 0.0591. So people, so instead of this 6 minus 7, I'm going to put the minus sign right here. Okay. So can I say I'll be getting the value as minus 0.197 plus 0.05 0.04591 is the value of the reduction potential of the same electrode when its pH is kept as 6. Yes, just calculate this value and let me know the answer in the chat box. Just calculate this value. Is it coming as minus 0.1379? Okay, the reduction potential of the electrode when the pH of the electrode is kept as 6 is coming as minus 0.13, how much? Minus 0.1379 volts. Yeah. So people, this is how the question was to be solved. Let me know in the chat box if the question is clear to every single guy right here. Let me know in the chat box first if it's clear to every single guy. Yeah. Yes. So these are not boards level questions, bro. These are JEE NEET, JEE Mains, JEE Advanced level questions. Yeah. So then class timing at JEE channel is 5:30 in the evening, and class timing at the NEET channel, in the NEET channel will be at 11 p.m. Yeah. Samala, you can do one thing. You can take the video a little back. It'll be a replay. Okay. It'll be automatically. Just take the video a little back. It'll be automatically a replay. Okay. Right. Okay. So people, should we move on to one more question? Should we move on to one more question? Let me know in the chat box if it's clear to every single guy right here. Should we move on to one more question? Let me know in the chat box. Let me know in the chat box. Yeah. Let me know in the chat box if you want me to move on to the next question right here. Okay. Let's move on. Let's move on. Let's move on to one more question right here. This is the question on our screen. See guys, I'm given with a reaction NO3 negative whose concentration is 1 molar. 2 times H positive aqueous plus 1 electron gives NO2 gas whose pressure is 1 bar, H2O liquid. Yes. People, first thing which you should notice right here, this is the reduction reaction because electron is being gained right here and the N value is equal to 1 because 1 mole of electron is being exchanged in the reaction. Yes. So if this is reduction reaction, which value it's going to be? It's going to be standard reduction potential value of the electrode whose reaction is this one. Yes. Calculate the reduction potential in the neutral solution when the pH is equal to 7. Again, we can kill this one, yeah? We can kill this one, right? See guys, how this question is to be solved. First of all, we are given with a balanced reaction right here. This is the reaction which is taking place at some electrode, yeah? So can I write, see, we got the value of N. We got the value of standard reduction potential. I simply need to write the expression for QC. Expression for QC is going to be equal pressure of NO2, which I call as partial pressure of NO2 raised par stoichiometry coefficient. This is in liquid form, its active mass is unity, divided by this in aqueous form. I'll be using its concentration. So concentration of NO3 negative raised par stoichiometry coefficient multiplied by concentration of H positive to the power 2, right? So people, what is the pressure of NO2? It's simply 1 bar divided by what is the concentration of NO3 negative? It's 1 molar. What is the concentration of H positive? Do we know the concentration of H positive? No, we do not know that. We are given with something called as pH. pH of solution is given as 7. If pH of solution is given as 7, I can say H positive concentration will be equal to 10 power minus 7 molar. Yes. So it's going to be 1 multiplied by concentration of H positive, I got to know as 10 power minus 7, is going to be a square. So the value will be simply coming as 10 power 14. I got the value of QC right here. Yes. Yes. Now, I got the value of QC. I got the value of N1. I got the standard reduction potential of the electrode whose cell reaction is this one. Can I simply use the Nernst equation? Absolutely. The question will be dusted right here. I can say the reduction potential will be equal to the standard reduction potential E naught RED minus 0.0591 divided by N and log of QC. Yes, this is my Nernst equation which I'll be using in order to calculate the Nernst equation. Yes, absolutely. People, is the standard reduction potential value given to us? Yes, it is 0.78. It is 0.78 minus 0.0591 divided by N value. Is the N value given to me? Absolutely 1. It's going to be log of QC. QC value is nothing, that is 10 to the power 14. Yes. So you'll be getting the value as 0.78 minus 0.0591 divided by N value is 1. Log of M to the power N, it's going to be 14. Log 10 is 1. Just solve it a bit and let me know the value of it exactly. Is it minus 0.047? Yeah. All right, it is minus 0.047 volts right here. So this is the reduction potential of the electrode whose cell reaction was given to us right here at the pH of 7, correct? Yes? People, is it clear to every single guy? Let me know. Let me know in the chat box if it's clear to every single guy so that I can move on to the next question. Yes? Wonderful. All right. Let's move on. Let's move on to one more question. Let me see if you can solve this one or not. This is one nice question, guys. How much does the reduction potential of the electrode change if H positive concentration is decreased from 1 molar to 10 power minus 4 molar at 25 degrees centigrade? This is one more question, but it's a bit lengthy question, yeah? It's a bit lengthy question. And this is one nice question, guys. See, first of all, I'm given with one electrode right here. What are we supposed to check? We are supposed to check how much does the reduction potential of the electrode decreases. How much does the reduction potential of this electrode decreases if the concentration of H positive is changed from 1 molar to 10 to the power minus 4 molar right here. Yes? Now guys, see how this question is to be solved. See how this question is to be solved. First of all, we need to check how much reduction potential decreases. Right? Right? So first of all, I'm going to write the reaction right here. Let me know the oxidation state of Mn right here is plus 7. Oxidation state of Mn right here is plus 2. So plus 7 to plus 2. Decrease in oxygen state. Decrease in oxygen state means reduction. Yes. So reduction means gain of electrons. So what is going to be the reaction which I'll be writing over here? It's going to be MnO4 negative. MnO4 negative aqueous. It will be gaining how many electrons? See guys, plus 7 to plus 2. What is the change in oxygen state? Change in oxygen state is 5. That means this MnO4 negative will be gaining 5 electrons right here. It will be gaining 5 electrons right here. Yes, and it will be getting converted to what? It will be getting converted to Mn di positive. Correct? Mn di positive. And people, it's mentioned in the question the reaction is taking place in the acidic medium. If it is taking place in the acidic medium, we know how to balance the reaction in acidic medium. Yes. Over here we have got 4 oxygens. So this is first of all aqueous. Okay. And over here we have got 4 oxygen atoms. In order to balance the oxygen atoms, we should add some water molecules. Yes. Now. Are the hydrogens balanced? Are the hydrogens balanced? Since oxygens are balanced, now it's time to balance the hydrogens. How many hydrogens do I have right here? It is 4 2s are 8. I'll be writing 8 times H positive aqueous right here. Now the reaction is balanced. Now the reaction is balanced, yeah? Correct? Now people, how to approach to this sort of equation? How to approach to this sort of equation? Understand. First of all, I'm going to write the expression for QC. I'm going to write the expression for QC. Can we write the expression for QC right here? It's going to be simply concentration of Mn di positive. Concentration of Mn di positive raised by stoichiometric coefficient divided by concentration of MnO4 negative raised by the stoichiometric coefficient multiplied by concentration of H positive to the power stoichiometric coefficient, that is 8. I got the QC value, right? I know the N value. N value right here is 5. Okay. Now people, I can simply write the expression of Nernst equation right here. I can simply use the Nernst equation expression. It's going to be reduction potential of the electrode is equal to E naught RAD. E naught RAD, standard reduction potential, minus 0.0591 divided by N. N value we got to know as 5. And it's going to be log of QC. QC value we got to know as concentration of Mn di positive. Concentration of Mn di positive is given to me in the equation, that is 1, divided by concentration of MnO4 negative, that's also 1. H positive concentration, is that given? Let me keep it as such, 1 divided by H positive concentration to the power what? To the power 8, because these two terms are equal to 1. Yeah. Now people, I can write it like this as well. This is going to be concentration of H positive to the power minus 8. Yes, I can write it like this. Correct? Now we will see. This is log of m to the power n. Now you can use the simple mathematics. It's going to be standard reduction potential minus 0.0591 divided by 5. Log of m to the power n will be n log m. So it's something like this, n log m. Yes. So I'm going to write it like this. Just have a look. I'm going to write the reduction potential of the electrode will be equal to standard reduction potential, which is E naught RAD. It is going to be plus 0.0591 plus 0.0591 multiplied by 8 by 5 multiplied by 8 divided by 5. Yes, and it's going to be log of H positive concentration. This is the general expression which we got. This is the general expression which we got for the electrode whose cell reaction is this one. This is the general expression for the reduction potential for the electrode whose cell reaction is this one. Yeah. Right? Now we will see. I'm going to use the conditions in the question. We need to check how much does the reduction potential of the electrode change if the H positive concentration decreases from 1 molar to 10 to the power minus 4 molar. Yes. Now people, if the concentration of H positive is kept as 1 molar, at that time, can I say reduction potential will be equal to the standard reduction potential of the electrode? Yes. Why is that? If I keep the H positive concentration as 1, log of 1 is 0, this whole term becomes 0. Yes. Right? Now people, see, if the concentration of H positive is changed from 1 molar to 10 to the power minus 4 molar, what will be the value of reduction potential at that time? I'll say reduction potential will be equal to E naught RED minus 0.0591 divided by N value we already know, that is 5, multiplied by 8. It's going to be log of H positive concentration, which is 10 power minus 4. Right? Now people, you'll get it like this. Reduction potential will be equal to E naught RED minus this value. When you will solve it, you'll be getting it as 0.382. You'll be getting it as 0.382 right here. Now people, understand one important thing right here. When the concentration of H positive was kept as 1 molar, at that time the reduction potential of the electrode was equal to the standard reduction potential. When the concentration of H positive is changed from 1 molar to 10 power minus 4 molar, can I say the reduction potential got decreased by this much amount? Yes. Yes. Absolutely. That's what we were supposed to calculate. When the concentration of H positive changed from 1 molar to 10 power minus 4 molar, I'll say reduction potential is decreasing. First it was equal to E naught RED. Now it is E naught RED minus something. Yes. So I can say right here, on changing the concentration of H positive from 1 molar to 10 to the power minus 4 molar, the reduction potential is decreasing by how many volts? By 0.382 volts. Yes. 0.382 volts. Yes. So this is something which we are supposed to calculate. How much does the reduction potential decrease? Yeah. So reduction potential is decreasing by 0.382 volts when the concentration of H positive is changing from 1 molar to 10 power minus 4 molar right here. Yes. Correct? Ashutosh, if you solve this term, its value will be simply 0.382. That's what I said, yeah? Right? So people, is it clear to everyone? Should I move on to one more question? Let me know in the chat box. Let me know in the chat box if you want me, guys, if you want me to move on to one more question right here. Yes. Let me have some water first. Okay. All right, let's move on to one more question. Let me see if you can solve this one or not. Okay, this is the question on our screen, guys. Have a look. We are given with two reactions. NO3 negative gives NO2 gas. One more is NO3 negative gives NH2OH. And both the reactions are taking place in acidic medium. We are given with some E naught values as well for both the reactions, right? At what pH will the two cells have same reduction potential? Assume the concentration of all these species to be unity. Yes. This is one more nice question, yeah? See how this question is to be solved. First of all, just a second, guys, just a second. Let me divide it into two, okay? First of all, the first reaction, if I'll consider NO3 negative aqueous, it is getting converted to what? It's getting converted to NO2 gas. Correct? People, if I ask you what is the oxidation state of nitrogen right here, you should say +5. Yes. What is the oxidation state of nitrogen right here? It is +4. +5 to +4. Is it increase in the oxidation state or decrease? It is decrease in the oxidation state. Decrease in the oxidation state is what we call as reduction. Reduction means gain of electrons. So over here there is a gain of 1 electron. Yes. And the reaction is taking place in acidic medium. Do we know how to balance the reaction in acidic medium? Yes, we know that. 3 oxygens, 2 oxygens. So I'm going to add 1 water molecule right here in order to balance the oxygen. Now people, are the hydrogens balanced? No way. Over here we have got 2 hydrogens. So I'm going to add 2 H positives. Right? I'm going to add 2 H positives right here. Yeah. This is the reaction. This is the complete reaction. This is the complete reaction, which is basically a reduction reaction. And we got to know the value of N right here in this reaction, which is 1. Yeah. So people, this value which is given to me, is it now the standard oxidation potential value or standard reduction potential value? It is the standard reduction potential value. Yeah. It is the standard reduction potential value, correct? Now similarly, if I'll consider the second reaction, which is NO3 negative aqueous, it gives, or let me write it like this, NO3 negative, it gives what? It gives NH2OH in the liquid form, yeah? Now first of all, let's try to balance this reaction. Let's get to know, is it oxidation reaction or reduction reaction? Then let's try to balance it. We can do that, right? See guys, how this question is be solved. First of all, the oxidation state of nitrogen right here is +5. What about the oxidation state of nitrogen right here? Let's assume the oxidation state of nitrogen is X. Hydrogen, it will show +1 oxygen state, and we have got 3 hydrogens. Yes, oxygen is going to show -2 oxygen state. Net charge is 0. So it's going to be X plus 1 is equal to 0. So X is -1. Correct? So nitrogen is having -1 oxygen state right here. Yeah. Nitrogen is having -1 oxygen state right here, correct? Now people, is the oxidation state of nitrogen increasing or decreasing? It is decreasing. Decrease in the oxidation state is what we call as reduction. Reduction means gain of electrons. So how many electrons are being gained by this NO3 negative right here? +5 to -1. What is the change in oxygen state? Final oxygen state, which is -1, minus initial oxygen state 5. So -1 minus 5, that is going to be equal to -6. Take the mod, that is 6. Yes. So 6 electrons are being gained by this NO3 negative right here. Yeah. Yes. Now. The reaction is taking place in the acidic medium, and we know how to balance the reaction in acidic medium. So first of all, over here we have got 3 oxygen atoms. Over here we have got only 1 oxygen atom. So I'm going to add 2 water molecules. Yeah. I'm going to add 2 water molecules. After adding 2 water molecules, I need to balance the hydrogens as well. Right? How many hydrogens are there on the right hand side? 3. 3 plus 4 is 7. So I'm going to add some 7 H positives right here. Yeah. I'm going to add some 7 H positive aqueous right here. Yeah. Now see guys how this question is to be solved. This is the reduction reaction. This is the reduction reaction. That means both these potentials are the standard reduction potentials right here. Now we need to check at what pH will the 2 cells have same reduction potential. At what pH will the 2 cells have same reduction potential. Okay. And assume the concentration of all the other ions, all the other species except H positives as unity. Yes, that's something which is given to me in the question. What I'll be using, I'll be first of all writing the Nernst equation. Reduction potential of the electrode whose cell reaction is this one is equal to E0 cell is 0.78 minus 0.0591 divided by N. N value is going to be as 1. It's going to be log of QC. Log of QC. Correct? QC is going to be pressure of this one, which is going to be unity. This is going to be unity, right? So 1 in the numerator divided by, this is going to be unity divided by H positive concentration to the power 2, because it's mentioned in the question, assume the active masses of all the other species except hydrogen to be 1. Yeah? Correct? Right? People, can I write it like this? 1 upon H positive concentration square. Can I write it H positive concentration raised power -2? Yeah? Now log of m to the power n, can I write it like this? N log m. Can I take this -2 to the front? Can I say it's going to be log of H positive? Yes? Right? So people, can I write it like this? The reduction potential of the electrode is simply going to be 0.78 minus 0.0591 divided by 1 multiplied by 2. Can I say minus log of H positive is what we call as pH? Yeah, that's what we call as pH. Correct? Correct? I got the reduction potential of this electrode equal to this one, equal to this thing. This is the reduction potential of this electrode, which I'm keeping as such. Yeah. Why am I keeping it as such? There is a reason for that. Now people, what about the reduction potential of this electrode which I have over here? Reduction potential of this electrode is equal to standard reduction potential, which is 0.73 minus 0.0591 divided by n value is 6, and it's going to be log of QC. QC, this is 1, this is 1, this is 1. So it's going to be 1 upon H positive concentration to the power 7. Because it's mentioned in the question, assume all the active masses of other species as 1 except hydrogen. Yeah. So 1 upon H positive concentration is power 7. I'm going to write it like this. This is going to be concentration of H positive to the power minus 7. Log of m to the power n means simply n log m. Yes. It's going to be minus 7 log of H positive concentration. Yes. So people, I'm going to write it like this. The reduction potential of the electrode will be equal to 0.73 minus 0.0591 divided by 6. It's going to be minus log of H positive simply pH. It's going to be 7 multiplied by pH. Yeah. Yes. People, this is one more equation which I got. Now, as per question, what we were supposed to calculate? At what pH will the two cells have same reduction potential? This is the reduction potential of the first electrode. This is the reduction potential of the second electrode. At what pH will the electrodes have same pH? Can I equate these two equations? This is equation number 1. This is equation number 2. From equation 1 and 2, what can I conclude? I can conclude something like this. I can simply say 0.78 minus 0.0591 multiplied by 2 multiplied by pH should be equal to 0.73 minus 0.0591 divided by 6 multiplied by 7 multiplied by the pH. Yes. Now guys, can you solve it? The question is done. We are supposed to calculate the value of pH, right? Correct? So what I'll be doing, just take this 0.73 on this side. It's going to be 0.78 minus 0.73. It's going to be 0.05. Okay, just take this pH on that side. It's going to be 0.0591. I have taken common. It's going to be 2 times pH minus 7 divided by 6 multiplied by pH. Correct? Or you can take pH also common. It's going to be, I'm writing it over here. Just, I need some space. It's going to be 0.05 is equal to, I'm taking the pH common. If I took the pH common, just remove this pH right here, it's going to be 2 minus 7 by 6, which is going to be 12 minus 7 is 5, so it's going to be simply 5 by 6, yeah? It's going to be simply 5 by 6, correct? So people, I can write the pH of the solution, at which the reduction potential of both the electrodes are going to be same. The pH at which the reduction potential of both the electrodes are going to be same is going to be 0.05 multiplied by 6 divided by what? Divided by 0.0591 multiplied by what? Multiplied by 5. Let me know its exact value which you are getting right here. Let me know its exact value, guys. Let me know its exact value which you are getting right here. You'll be getting the value around 1.12. So people, at 1.12 pH, both the electrodes are going to have the same reduction potential over here. Let me know in the chat box if it is clear to everyone so that I can move on to one more nice question right here. Let me know in the chat box. I'm waiting for your answers. Let me know in the chat box fast. Yes. Let me know in the chat box. Yeah. Okay. I'm moving on to one more question, guys. This is one more question on our screen. Now we are going to calculate the EMF of a complete cell. Calculate the EMF of a complete cell, right? I'm given with a complete cell which has got two electrodes. Okay. I've got a complete cell which has got two electrodes. This is the first electrode, this is the second electrode, and in the middle, these two lines, they represent the salt bridge. Remember, on the left hand side of the salt bridge, we always write anode. On the right hand side of the salt bridge, we always write cathode. Yeah. Now, people, how this question is to be solved? Understand properly. See, first of all, I'll be writing the reaction which will be taking place at anode. You can easily write that. Reaction which will be taking place at anode is going to be tin solid gets converted to Sn di-positive aqueous plus how many electrons? Plus 2 electrons. This is the reaction which is taking place at anode, because we know tin gets converted to Sn di-positive, yes. Similarly, can I write the reaction which will be taking place at cathode? Absolutely, we can do that. The reaction which will be taking place at cathode, can I say it's going to be Pb di-positive aqueous, Pb di-positive aqueous plus 2 electrons should get converted to Pb solid. This is the reaction which is taking place at cathode, reduction reaction, yeah? Yes. Now people, in order to write the net reaction, I need to make the electrons balanced in both the reactions. And electrons are already balanced in both the reactions. When I'll add these two reactions, can I say this 2 and this 2 will get cancelled, and number of electrons which will be getting cancelled out while adding the two reactions, that gives you the value of N. That gives you the value of N right here for the complete cell, yeah? Now guys, can I write the net cell reaction? It's going to be tin solid plus Pb di-positive aqueous plus Pb di-positive aqueous. It gets converted to Sn di-positive aqueous plus Pb solid. Yes, this is the net cell reaction which is taking place in this cell, in this complete cell right here. Yes, I got the value of N as well. Now the point is, what is the value of Qc? Qc value is simply concentration of Sn di-positive multiplied by concentration of Pb solid, which will be simply 1, yes, divided by concentration of Pb di-positive. What is the concentration of Sn di-positive? It is 1. What is the concentration of Pb di-positive? It is 10 power minus 3. The value is going to come as 10 power 3. So I got the value of Qc as well. I got the value of Qc as well. People, you got the value of Qc. You know the value of N. It's time to calculate one more thing, which is the E naught cell. Remember, E naught cell is always standard EMF for this cell will be equal to E naught of cathode minus E naught of anode. Standard EMF for this cell is always equal to E naught of cathode minus E naught of anode. And for cathode and anode, I'll be taking their respective standard reduction potential values. This E naught C right here will be the standard reduction potential of cathode. E naught A will be the standard reduction potential of anode. Yeah, I'll be taking the standard reduction potentials of both these electrodes right here. Now first thing, what is my cathode? Cathode is this tin electrode. Am I given with the standard reduction potential of this tin electrode? You can check it out. Plus 2 to 0, that means reduction. Reduction means this is the standard reduction potential value of tin electrode. So this is the value of E naught C, right? E naught cathode, correct? Similarly, is this the standard reduction potential value? Again, plus 2 to 0, reduction. That means this is the standard reduction potential value of anode. Correct? This is the standard reduction potential of value of anode. This is the standard reduction potential value of cathode. Yes. So people, can I calculate the E naught cell standard EMF for this cell? Absolutely. E naught of cathode, which is going to be minus 0.14 minus E naught of anode. E naught of anode is going to be minus 0.13. Correct? So I got both the values, E naught of cathode, E naught of anode, correct? What is the exact value which you'll be getting from here? It's going to be minus 0.01. So you got the E naught cell value, standard EMF of this cell right here. People, we have all the values. We are supposed to calculate the EMF of the cell. Can we do it? Absolutely, we can do that. We can write it somewhat like this. Just a second, guys. Just a second. I think I did the reverse, yeah? I did the opposite. Just a second. E naught of cathode, E naught of cathode. E naught of cathode is minus 0.14. E naught of cathode is minus 0.14 minus E naught of anode. E naught of anode. No, I was correct, yeah? It was correct. It was correct only. So it's going to be minus 0.01 volts, yeah? Now, I'm going to use the Nernst equation, which will be equal to E cell. EMF of the cell is equal to E naught cell. Standard EMF of the cell, minus 0.0591 divided by N. It's going to be log of QC, yeah? So guys, I can calculate E cell from here. I can calculate the EMF of the cell. It's going to be equal to E naught of cell is equal to minus 0.01 minus 0.0591 divided by N value we have already got, that is 2 log of QC. What is the value of QC which we have got already? That's 10 power 3. Can you solve this one and let me know the exact value of the EMF of this cell which we were supposed to calculate? It's going to be minus 0.01 minus 0.0591 divided by 2 log of m to the power n, which is n log m, right? 3 log 10 is 1. People, just solve it out. Let me know the exact value of it in the chat box. Harry is saying it is minus 0.07. Is that Harry? Is that? Okay, so EMF of the cell is coming out to be minus 0.07 volts right here, which we were supposed to calculate. People, is it clear to every single guy? Let me know in the chat box so that I can move on to one more question. Let me know in the chat box if it's clear to everyone so that I can move on to one more question right here. Yeah? Should I move on to one more? Yes? Wonderful. All right, I'll be giving one class on calculations as well. No issues, no issues. Thank you, Rajesh. Thank you. Okay, let's move on. Let's move on to one more question, guys. Determine the EMF of the cell. Again, the same type of question, guys, but only one concept. Only one concept involved in the question. See, we are supposed to calculate the EMF of the cell which is given to us. Yeah, we are supposed to calculate its EMF, correct? Now, people, these two lines in the middle, this represents your salt bridge. On the left hand side of the salt bridge, we have anode. On the right hand side of the salt bridge, we have cathode. Yeah. And people, at anode, we know oxidation takes place, and at cathode, we know reduction takes place. Yeah. So first of all, in order to calculate the EMF of the cell, I should write the reaction at anode, then I should write reaction cathode, then I should add them up. I'll be getting the net cell reaction. Yes. Now, how to solve this one? How to approach to this sort of question? Understand? I'm going to write something like this. First of all, I'll be writing the reaction which will be taking place at anode. H2 is getting converted to H positive. So I'll be writing the reaction as H2 gas gets converted to 2 times H positive aqueous plus how many electrons? Plus 2 electrons. This is the reaction which will be taking place at anode. Now, what about cathode? Fe tripositive is getting converted to Fe dipositive. Yes. So at cathode, Fe tripositive aqueous will be gaining 1 electron and it will be getting converted to Fe dipositive aqueous. Yes, this is the reaction which I got. Yeah, these are the two reactions which are taking place at the anode and cathode respectively. Yes. Now we will see, can I simply add these two reactions? I cannot add the two reactions right now, because in order to add the reactions, the electrons should be balanced on both the sides. Are the electrons balanced? No way. I need to balance these. So I'm going to multiply the second reaction by 2 so that electrons will be balanced on both the sides. After multiplying the reaction, second reaction by 2, I'll add them up. Yeah. So I'll be getting something like this. H2 gas plus 2 times Fe tripositive aqueous plus 2 times Fe tripositive aqueous, it gets converted to 2 times H positive aqueous plus how much? Plus what? Plus 2 times Fe dipositive aqueous. Yes. This is the net cell reaction which I got right here. People, can you let me know the value of N? Can you let me know the value of N right here? Can you let me know the value of N right here? What is the value of N? Let me know first. What is the value of N? How many electrons got cancelled? 2 electrons got cancelled. Yeah. So the value of N which you got right here, it's simply 2. Yes, N value is 2. Correct? Wonderful. Can you write the expression of QC right here? Absolutely. It's going to be concentration of H positive, which is given to me as, concentration of H positive is given to me as 10 power minus 3. So it's going to be 10 power minus 3 raised power stoichiometric coefficient, that is 2. What is the concentration of Fe dipositive? That is given as 0.01. That means 10 power minus 2. Yeah. 10 power minus 2 raised power stoichiometric coefficient, that is 2, divided by. What is the pressure of H2? Pressure of H2 is given as 0.1 bar, which is 10 power minus 1. Raised power stoichiometric coefficient, that is 1. What is the concentration of Fe tripositive? That is again 0.1. That means 10 power minus 1 raised power stoichiometric coefficient, that is 2. What is the value of QC which you are getting from here? I can say you are getting the value as 10 power minus 6 multiplied by, this is 10 power minus 4 divided by, this is 10 power minus 1 and multiplied by 10 power minus 2. In the numerator, you are getting 10 power minus 10. In the denominator, you are getting 10 power minus 3. So you are getting the value as 10 power minus 7. This is the value of QC which you got right here. Yes. So people, I got the value of QC, I got the value of N. Yes. Now, what am I supposed to calculate? I'm supposed to calculate E naught cell now. Yes, I can do that. E naught cell is simply going to be equal to E naught of cathode minus E naught of anode. Yes. I need to take the standard reduction potential values of cathode and anode right here. Yes, I can do that. Now, people, your hydrogen electrode is the anode and your Fe tripositive and this ionic electrode is your cathode right here. Yes. So I'll be writing the standard reduction potential of cathode. Am I given with the standard reduction potential of cathode? This is my cathode first of all. This is my cathode first of all. Am I given with the standard reduction potential of cathode? No way. Why is that? Because right here oxygen state is +2, right here is +3. Increase in oxygen state is what we call as oxidation. So this is basically the standard oxidation potential. But do I need the standard oxidation potential of cathode or standard reduction potential of cathode? I need the standard reduction potential of cathode. So I'm simply supposed to reverse the sign. Yes. Minus standard reduction potential of anode. Since this is the hydrogen electrode, so its standard reduction potential value is 0, as you all must be knowing. So I got the value of E naught cell as well. Yeah, I got the value of E naught cell as well. People, you got the E naught cell value, you got the expression for QC, you got the value of N. You can simply use the Nernst equation right here. Yes, you can write EMF of the cell will be equal, it must be equal to E naught cell minus 0.0591 divided by N, and it's going to be log of QC. Everything you have calculated, you can put all these values into this equation. You'll be getting what? You will be getting the E cell, yeah? Right? So people, E cell is equal to E naught cell value, that is 0.17 minus 0.0591 divided by N. N value is given as 2. Yes, we got to know that. Log of QC. QC value we have already calculated as 10 power minus 7. There is a bit of calculation needed. The question is done and dusted. 0.0591 divided by 2. Log of m to the power n is n log m. Log 10 is 1. Yes. So it's going to be 0.17 plus 0.0591 divided by 2 multiplied by what? Multiplied by 7. Just solve it out. Let me know the answer in the chat box fast. Let me know the answer in the chat box, guys. Fast, fast, fast. Solve it out. Solve it out. Solve it out. Let me know the answer in the chat box. Let me know the answer in chat box. Rashid is saying it's coming as 0.37. Okay, Angela is saying the same. Harry is saying the same. Wonderful. So 0.37 volts is the value of EMF of the cell. Now let me know in the chat box if it's clear to everyone right here. Let me know in the chat box fast. If it is clear to everyone. Yeah? Yes? Should I move on to one more question? Hi Abdul Hadi, how are you doing? Should I move on to one more question right here? Yeah? Okay, let's move on. Let's move on to one more question which is on our screen. A very, very simple question. The question was once asked in your JEE. People, can you solve it out? Can you solve it out? Can you let me know the answer in the chat box? Can you give it a try? Can you give it a try? Can you give it a try? Let me know the answer in the chat box fast. Yeah? Yes. Thank you, Basit. Thank you. Charan, you do one thing, you just change the quality of the video. It's perfect from my side. Guys, is the board blur or something? No? Guys, is the board blur or something? Let me know fast. Okay, now we will see how this question is to be solved. It's again a very simple question. We are given with the EMF of the cell. EMF of the cell is given as 0.81 volts, yeah? EMF of the cell is given as 0.81 volts. And the cell which is given to us as M changed to Mn positive, whose concentration is this. H positive, whose concentration is 1 molar, changed to H2. The pressure of it is 1 bar. Calculate the charge present on the metal. We are supposed to calculate the value of N right here. Correct? And we are given with the EMF value as well. EMF value is given to us from the question. Yeah? So we will see how this question is to be solved. First of all, this is the salt bridge. These two lines, it represents your salt bridge. On the left hand side of the salt bridge, we always write the anode. Yeah? And at anode, we know oxidation takes place. So can I say metal solid will get converted to Mn positive aqueous plus how many electrons? Plus N electrons. This is the reaction which is going to take place at anode, right? Yes, this is the reaction which is going to take place at anode. Now similarly guys, I can write the reaction at cathode. At cathode, reduction takes place, H positive gets converted to H2. So the reaction must be like this: 2 times H positive aqueous plus 2 electrons, it gets converted to H2 gas. It gets converted to H2 gas, right? Now can I add these two reactions? The first reaction is taking place at anode, the second reaction is taking place at cathode. Can I add these two reactions directly? No way, because the electrons are not balanced yet. Let's try to balance the electrons. I'm going to multiply the first reaction by 2 and I'm going to multiply second reaction by n. Yes? So after multiplying the reactions by 2 and n respectively, then we are going to add them. Yes? And when we add them, you are going to get it as 2 times metal solid plus, it is not going to be 2, it is going to be 2n times H positive concentration, 2n times H positive aqueous right here. Yes? It gets converted to, this is going to be 2 times Mn positive aqueous plus what? Plus n times H2 gas, right? This is the net reaction which takes place in the cell which is given to us, yeah? Right? Now people, can you let me know the value of n? Is it going to be n or 2n right now? Can I say the number of moles of electrons which are exchanged in the reaction right here, in the net cell reaction, that is going to be 2n, that's not going to be n, because 2 and 2n will get cancelled out, yeah? Yes, do you agree with that? Absolutely, yes. I got the value of electrons exchanged. Now guys, can I write the expression for QC as well? QC expression is going to be concentration of Mn positive raised power 2 multiplied by, this is going to be partial pressure of H2 raised power n divided by, this is solid, its active mass is 1, so it's going to be concentration of H positive raised power 2n. Yes. Do we know these values, guys? Do we know these values? Let's check it out. Concentration of Mn positive is given to me as 0.02. So I'm going to write 2 into 10 power minus 2 raised power what? Raised power 2 multiplied by. What is the partial pressure of H2? That's given to me as 1 bar. Okay, so nothing to do with this. Divided by what is the concentration of H positive? Concentration of H positive is 1 molar, 1 raised power anything is 1. Yeah. So I got the value as 4 into 10 to the power minus 4. This is the value of QC which I got. Yeah. People, do we know the E naught cell value? Let's get it. Let's get the value of E naught cell as well. E naught cell value will be equal to E naught of cathode minus E naught of anode. E naught of cathode minus E naught of anode. Yes. The cathode is your hydrogen electrode. Its standard reduction potential will be 0 minus standard reduction potential of anode. Standard reduction potential of anode. Is this standard oxidation potential of anode ki standard reduction potential? See guys, 0 to plus n. Increase means oxidation. That means this is standard oxidation potential. But do I need the standard oxidation potential of anode ki standard reduction potential? So for that I need to reverse this sign, right? It's going to be, value is going to be 0.76 only. So I got the E naught cell value, I got the QC value, right? I know the value of electrons exchanged. So what I'll be doing right here, I'll be using everything in the Nernst equation, and the Nernst equation is going to be E cell is equal to E naught cell minus 0.0591 divided by, is it going to be n or 2n? It's going to be 2n right now, and right here it's going to be log of QC. Correct? People, E cell, EMF of the cell is given to me as 0.81 volts, if you remember, yeah? It's given as per the equation, is equal to E naught cell value, I got to know as 0.76 minus 0.0591 divided by 2n log of QC. Log of QC. QC value is nothing, it is 4 into 10 to the power minus 4 right here. Yes. Right. Right. Now people, it is just the calculation part left. We are done with the question actually. Let's do the calculation part. 0.81 minus 0.76, that means 0.05 is equal to minus 0.0591 divided by 2n. Log of m into n. It's going to be log of m plus log n. Log 4 is 0.6 and log of 10 power minus 4 is simply minus 4. Yes. Right? Simple by using the property of log, that's it. Yeah. So people, just take this 2n on this side, or I can write n is equal to, minus 0.0591 divided by 2 multiplied by 0.05 multiplied by, this is going to be minus 3.4. Yes. So people, Approximately this and this will get cancelled out approximately, yes, and you'll be getting the value of n right here around as in 1.9 something, yes. N value is 1.9, so I have to take the n value as 2 right here because n cannot be fractional, charge cannot be fractional. So which integer is closest to this 1.9? That is 2. So the n value right here will be 2, and what is n? That is the charge present on this m right here, which we were supposed to calculate. Let me know in the chat box if it is clear to everyone right here. Let me know in the chat box if you want me to move on to the next question. Let me know fast. Let me know fast. Let me know fast. Exactly, guys. N is equal to 2 is the answer. Yeah, correct. Absolutely correct. That's great, Sudan. That's great. That's wonderful to hear. That's wonderful. All right, Kamran, I'll be taking the class on calculation as well. No issues. Okay. So people, let's move on. Let's move on to one more question, which is on your screen. Can you solve this one, guys? What do you think? Can you solve this one? Can we solve this one right here? Yes, guys. Calculate the mass of NaOH required to be added to cathode to consume all the H positive ions in the following cell. Yeah? We need to calculate the mass of NaOH which must be added on the cathodic side so that all the H positive ions are consumed. Okay? How to solve this sort of equation? See, guys. See, how will I be solving this question right here? First of all, I'm given with the cell. Over here, this is the salt bridge. On the left-hand side of the salt bridge, always anode is written. On the right-hand side, always cathode is written. So what is going to be the reaction which will be taking place at anode? It's going to be zinc solid changed to what? It changed to Zn di positive aqueous plus how many electrons? Plus 2 electrons. This is the reaction which will take place at anode, yeah? Similarly, what is going to be the reaction taking place at cathode? It's going to be, since the cathode is hydrogen electrode, so when hydrogen behaves as the cathode, the reaction which should take place at the cathode of hydrogen is going to be twice H positive aqueous plus 2 electrons changed to what? Changed to H2 gas. This is the reaction which will take place when hydrogen will be acting as the cathode. People, are the electrons balanced on both the sides? Yes, electrons are balanced on both the sides. I can simply add these two, yeah? I can simply add these two, right? So after adding these reactions, can I get it something like this? Zinc solid plus 2 times H positive aqueous, it gets converted to Zn di positive aqueous plus H2 gas plus H2 gas. This is the net reaction which we have right here. Yes, I got the net cell reaction. People, can you let me know the value of N? Value of N is 2 because 2 electrons are being exchanged right here, or you can say 2 electrons are being cancelled right here, or you can say 2 moles of electrons are being exchanged in the net cell reaction, yeah? Yes? Yes. Now guys, see, can I write the expression for QC? Can I say QC expression is going to be concentration of Zn di positive raised per stoichiometric coefficient multiplied by partial pressure of H2 raised per stoichiometric coefficient, that is 1, divided by concentration of H positive raised per 2. Yeah. What is the concentration of Zn di positive which is given to us? That is 10 power minus 1. Multiplied by, what is the partial pressure of H2 gas? Is it given to me? No, I'm going to assume it as 1 atm, yeah? Okay. Divided by H positive concentration. H positive concentration, is that given to me? Yes, H positive concentration. People, there is something missing in the equation. Just a second. There is something missing in the equation. There is something missing in the equation. Okay. No. It's perfect. It's perfect. H positive concentration, I'm going to write as such, cos square. Yes. So QC value I got to know as 10 power minus 2 divided by concentration of H positive. Correct? Cos square. Correct? Now guys, how to approach to this sort of question after this, right? Volume is given. Absolutely, volume is given. Now we will see N value we got, QC value we got in terms of H positive. Yes. E cell value is given to us. People, can we calculate the E naught cell right here? Yes, we can calculate the E naught cell. People, let me tell you, E naught cell value will be equal to E naught of cathode minus E naught of anode. Cathode is hydrogen electrode. Its standard reduction potential will be 0 minus standard reduction potential of anode. is this the standard reduction potential of zinc? Standard oxidation potential. This is standard oxidation potential of zinc from 0 to +2, yeah? So its standard reduction potential will be minus 0.76, yeah? It is minus 0.76. The value is going to come as 0.76. I got the value of E naught cell, yeah? Now, what I'll be doing? I'll be using the Nernst equation, correct? And what is my Nernst equation all about? E cell is equal to E naught cell. Or let me write the exact values. E cell, which is given to me, E cell is given to me as per the question. Where is that? I think E cell is given to me, correct? E cell is given to me as 0.701 is equal to E naught cell. It is 0.76 minus 0.0591 divided by N value is 2 and the log of QC. QC value I got to know as 10 power minus 2 divided by H positive concentration ka square right here. Correct? Yes. Why I have taken minus 0.76? Because right here E naught cell is equal to E naught of cathode minus E naught of anode. For cathode as well as anode, I need to take their standard reduction potentials. Standard reduction potential of anode. Standard reduction potential of anode. Standard reduction potential of anode. Right? Standard reduction potential of anode. This is the standard oxidation potential of anode. That's why I reversed its sign. It got converted into standard reduction potential. Okay. And over here, I took the standard reduction potential of anode. And this is the standard reduction potential of cathode, which is your hydrogen electrode right here. Yeah. Got it? Yes. Now we will see. When you will solve this equation right here, I guess you'll be getting the H positive concentration or no. You'll be getting something like this. You'll be getting log of H positive. You'll be getting log of, after solving this equation right here, at the end you'll be getting log of H positive for somewhere as minus 1.5. This is something which you'll be getting at the end when you will solve it, okay? So I can say the H positive concentration right here is going to be simply anti-log of minus 1.5. Yes. People, do you know how to take the anti-log? Right? What I'll be doing, I'll be simply breaking it into two parts. I'll be writing it in the form of anti-log of minus 2 plus 0.5. Minus 2, I'm going to write simply as 10 power minus 2. 0.5 is the value of log 3. So I got the H positive concentration right here as 3 into 10 power minus 2. Yeah. I got the H positive concentration as 3 into 10 power minus 2. So people, I got the H positive concentration in the cathode as 3 into 10 to the power minus 2. We know H positive concentration is nothing. It is number of moles of H positive divided by volume. This value is given as 3 into 10 power minus 2. So from here, can I calculate the number of moles of H positive? It's going to be 3 into 10 power minus 2 multiplied by volume is 1 liter. So number of moles of H positive in the cathodic container is 3 into 10 power minus 2. Yes. What are we supposed to calculate? We are supposed to check what is the mass of NaOH that must be added to the cathode in order to neutralize all the H positives. In order to neutralize all the H positives in the cathode, can I say number of moles of OH negative added should be equal to number of moles of H positive in the cathodic container? Yeah. Then only neutralization can happen. Then only NaOH, then only OH negative or NaOH is going to neutralize all the H positives present in the cathodic container. Yeah. Absolutely correct. Now we will number of moles of OH negative. Instead of number of moles of OH negative, I can write it like this, number of moles of NaOH, because OH negative is coming from NaOH only. Yeah, it's going to be same thing. I can say number of moles of OH negative added to the cathodic container should be equal to number of moles of H positives present in the cathodic container. Now number of moles of NaOH, I can write mass of NaOH added to the cathodic container divided by molar mass of NaOH added to the cathodic container. It's given to us as number of moles of H positive we got to know as 3 into 10 power minus 2. Yes, molar mass of NaOH, all of you must know that is 40 grams per mole. So can I say mass of NaOH which is to be added to the cathodic container in order to neutralize all the H positives will be equal to 40 multiplied by 3, which is 120 into 10 to the power minus 2. It is going to be 1.2 grams. So people, we need to add 1.2 grams of NaOH to the cathodic container, then only all the H positives will get neutralized. I hope you got this question. This was a bit lengthy one, yeah? And this was asked in your advanced ones, yeah? So should I be moving ahead? Should I be moving ahead? Exactly, Rashid. 1.2 grams of NaOH are supposed to be added on the cathodic container. Then only complete neutralization will happen. Then only NaOH is going to react with the entire H positive which will be there in the cathodic container. Yeah. Correct? Vahik, I didn't get you, bro. What are you saying? I didn't get it. I didn't get what you're saying. Saad, it depends on your preparation, bro. Like, how is your preparation? If you think it's not up to mark, you cannot. If you think, I mean, you get that feeling from inside, right? If you think really that you're not going to, I mean, kill it in the first attempt, then it's definitely better to take a drop. There is nothing wrong in that. There is nothing wrong in that, as for me. Yeah. Yes, Said, you can do that. Okay.